All right, welcome everyone to the September 2022 meeting of the Memphis Astronomical Society. Once again, I'm your host, Jeremy Veldman, and we got another outstanding program for you guys tonight. The James Webb Space Telescope has been in the news quite a bit the last month or two, and you're going to hear an update from one of our best teachers, so be sure you stick around for that. But before we get started, let me cover a few preliminaries here. So again, we are the Memphis Astronomical Society. We are a nonprofit public service organization promoting interest in education in astronomy and related sciences. And our website is memphisastro.org. You can find us on Facebook. We've got a group. And once again, if you haven't already, please take a moment to subscribe to our YouTube channel. We've got videos from some of our past meetings as well as other events that we've done. So check that out if you're new to our group, and be sure you subscribe to this channel. Now, if you'd like to be added to our email distribution list, simply go to our website, memphisastro.org, and click the join button. You can see two different places here. Brings up a separate form, just fill out your details, and we send out updates about once a week regarding upcoming events, whether it's meetings like this or various outreach events, or of course observing sessions when it's clear. So it's a great way to stay engaged with us. If you're not on our email list already, please click the join button and you'll be added to our email distribution list. And for outreach, again, we do various events around town, whether it's observing with our telescopes or presentations, teaching, just anything related to astronomy. You can schedule that by going to the contact form and clicking the down menu here, schedule talk and or telescopes, and it'll bring up a separate form. This just really helps us get familiar with your group and your needs and basically how we can best serve you. So that's the best way if you're looking for our services or any future outreach requests. Okay, cover real quickly here the calendar of events for the month. And most of the action is toward the end of the month. We're transitioning here from summer into fall. And you can see here on the 9th, we got a meeting tonight. And of course, tomorrow night, not a whole lot going on. We got a full moon. And I think the weather is a little iffy as far as possibility for cloud cover. But next week, the 17th, again, we're on the back end of the moon cycle. So we are planning to have a session at Burton's if it's clear. So stay tuned to your email for that notice. Our next dark sky observing session at Burton's will be Burton Sugar Farm will be next Saturday, September the 17th. A group is going to be at Pinson Mounds also. They've got an Archeo Fest, and there's no observing. It's basically a weekend event, and I think we're going to have a booth set up over there. So if you need to get out, you can go check that out. I think we'll have a scope there for solar observing. So we'll send notices out regarding that, just another outreach event or outreach opportunity, if you will. But if you're looking to do some observing, next Saturday, the 17th, will be our next dark sky event. And now this is a big one. 2 weeks from tomorrow, September the 24th, is our semi-annual Village Creek Star Party. I'm going to talk more about that in just a second. But before I do, the week after that will be at Bobby Lanier Farm Park. That's in town. We did something there back in May. Had a great turnout, a lot of telescopes, centrally located, near Germantown. So if you're in town in Memphis and you don't necessarily want to travel to either participate in or view, objects through our telescopes, you can come out to that event last day of September the 30th. That's Bobby Lanier Park. And that's also International Observe the Moon Night. So we've got that planned for Friday the 30th. And then the following Saturday, October 1, is the rain date. So if we're clouded out on the 30th, we'll try again the following Saturday. So again, we'll send out notices as we get closer to this date. That's at the end of September. But real important, on the 24th, we have our semi-annual Village Creek Star Party. And again, we do this every 6 months in the fall and the spring. The big outreach event at Village Creek State Park near Wynne, Arkansas. And we have an indoor program with sky charts and basically an overview of the objects we'll be looking at for the night. And then several telescope operators will be on hand to set up and show people objects through the nights, through their telescopes. We have small, medium, and high power. We try to organize this as best we can. Some of you may have seen the email notices already. We send different documentation out regarding the protocol. Just, we try to have too much structure, but enough in place so that it's organized. And I know several people have volunteered to bring their telescopes. We're hoping for a good turnout this year. So if you can bring your telescope, we'll take it. The more, the merrier. If you've already volunteered and emailed Mark Matthews, thank you. We're looking forward to, making this a great event. And you don't have to email Mark, just show up and bring your telescope if you want to. And again, if you don't have a telescope, you can come on out and view, or if you'd like to be a guide, we'll do that too. We have a crowd of people. Sometimes we get as many as 50 to 100 people that show up from around the community. We always need people to serve as guides and help, herd the crowd, if you will, through the maze of telescopes. You can kind of see how it's set up here. Basically, we park in this area. We start off with low power and then migrate to medium power and then the high power telescopes. So it's a unique opportunity for people, especially those who are brand new to telescopes, to get a view through several different types of telescopes and really get a good sample, if you will, of different celestial objects through different telescopes. So big outreach event. Again, it's located, it's about an hour's drive due west along I-40. If you're heading toward Little Rock, Arkansas, and exit 242 is Forest City. We meet there at Delta Q. Some of us do around 5:15, give or take, for supper. So if you're interested in doing that, feel free to come on out. You could email us ahead of time so we can get a head count. We don't know if 5 or 50 people are going to show up, but the main event starts a little after 7 o'clock. That's up at the Visitors Center here. Again, Village Creek State Park near Wynne, Arkansas, a little over an hour's drive. Nice exit. So if you want to get a hotel and stay the night, you can, but you can also make it back to Memphis. It's just a little over an hour's drive. So again, 2 weeks from tomorrow, September 24. Again, this is weather dependent. So we'll send the go, no go notice the day of, maybe the day before. So if we're clouded out, we'll reschedule in November. But if we're clear, then it's definitely a go, and plan on coming out, whether you can bring a scope or, participate, or just you want to look through our telescopes. So that's our semi-annual Village Creek Star Party. And another event that we've got coming up, and again, this is looking ahead to next month, the Arkansas Dark Sky Festival. And I think this is the first one that they've done. This is at the Tyler Bend Campground. I am planning to go. I'm not exactly sure what to expect. I'm not even sure they know what to expect because it's kind of novel, but the Memphis Astronomical Society is a participant in this event, along with several other groups, other astronomical societies, and Explore Scientific, who makes a lot of telescopes, eyepieces, different accessories for observing. They're going to be on hand. So this could be an interesting event. And it's just another opportunity to do something, not only in terms of outreach, but be at a dark sky location. And their website, you can see down there, Arkansas, darkskyarkansas.org. Again, we're participating in this. This is not necessarily astronomy. It's more, environmental, and making people aware of the growing problem of light pollution and preserving the dark sky as a natural resource, similar to the national park movement. So could be very interesting. I am planning to go. You can kind of get an idea of the location here. You could bring a scope if you want to. As far as lodging, there's a lot of people who've already signed up ahead of time. So this is kind of a camping thing. You bring a tent or you sleep in your car. I'm not sure what else is around there. I know there are some hotels. I'm not familiar with the area as well, but you can check out their website and, just come on out if you want to. And I know I'm planning to go. Maybe one or two other of us are planning to go as well. We'll see. but that's coming up October 21 and 22. So just keep that in mind if you're interested. All right, want to take a moment to welcome some of our new members. Freddie Howell, approved a couple days ago. Welcome to the Memphis Astronomical Society. As well as Haram Joshi. I apologize if I butchered that name. I know you're friends with Sarita, and just want to welcome you again to the Memphis Astronomical Society, as well as Lily Obenauer and Christopher Armour. So just kind of give you a virtual applause and say thank you. Welcome to our society, and we're looking forward to having you on board and seeing you at a future meeting or outreach event. And again, if you're a member, be sure you check out this month's Meteorite. If you are a newly subscribed member and you didn't get this month's edition, just reach out to us. I've got these on hand. I'll be happy to send you the latest edition. I've also got past issues if you want to view those as well. But again, for subscribers and paying members, check out this edition of our newsletter, which is the Meteorite. And you can also join us on Slack. I will send an updated link out. I think this link is expired. It's good for only 30 days. So, but Slack is the site that we use it's another channel, if you will, for correspondence. We do this with the board. We do this with our astrophotography group meeting. And we have a general MAS Slack site. It's just a way for people to communicate, ask questions, get some of your questions answered. Just look for any information on astronomy in general, and just really another way for us to collaborate. So again, we'll send an update out on this in the next couple of days, and that's another way for you to get involved or to engage with us if you would like. Okay, that should say September. Sorry, I didn't update the slide, but just a couple of news items to keep you guys up to speed on for Astro News. And of course, you're aware the Artemis 1 launch was originally scheduled for August 29. It's been scrubbed twice. We're not sure when the new launch date is, but when we do have that set, we'll go ahead and do a live stream, just like we did for the rollout and then also the first launch attempt. So it's just another reminder that this is a complex mission, got a lot of moving parts. You know, don't view a rocket as a single entity. View it as a combination of different systems, and they all have to work in concert or it's a no-go. So yeah, okay, great. I just got the new link for Slack. I'll send this out to everyone. Thanks, Ann. Anyway, so this was scrubbed for the first couple of times, and it could be as soon as mid-October, or it could be later than that. There are different launch windows. Eventually it will launch, and it will be quite an event when it does, but we'll send out updates when it happens. You know, scrubs, for people who are prisoners of instant gratification, it could be a little discouraging, but as NASA Administrator Bill Nelson reminded us, there were some shuttle missions that were scrubbed 20 times before they were finally launched. So this is not unusual. But anyway, we'll keep an eye out for updates on the Artemis 1 mission. And speaking of Earth and Moon, the first image of Earth from the moon was taken on August 23rd, 1966. And you can see here, this was, of course, before the Apollo missions. NASA Lunar Orbiter 1, 236,000 miles from Earth. And there were 5 orbiters that were actually launched during the early 1960s, leading up to the Apollo missions and really in preparation for Apollo. So, and you can see below in the lower right, a digitally enhanced version using modern technology of that particular image. We've come a long way in a little over half a century, but this is an iconic image, and it's fascinating to look back on that period of time and the progress that was made, and ultimately where we are today as a result of the silicon integrated circuit revolution. So that was in August of 1966. And Frank Drake has passed away at the tender age of 92 years of age. And for those of you who do know or don't know, Frank Drake was the one who kind of led the search for life on other planets elsewhere in our galaxy. And he actually came up with an equation named after him called the Drake equation for estimating the number of civilizations just in our own galaxy that have the possibility for habitable life. He was an optimist. I believe he and Carl Sagan in the early 60s estimated as much as 1 million different worlds potentially that could be habitable within our galaxy. And he was convinced that one day human beings would eventually connect with extraterrestrials. I'm a little skeptical, but when you in a galaxy of hundreds of billions of stars, 1 million sounds like a big number. If we had $1 million today, you could probably stop working for a while, maybe forever. But in a galaxy of 200 billion stars and possibly as many as 1 trillion planets, if you think about it, 1 million is really not that big a number. And that's an optimistic estimate. Scale that down by a couple of factors, 100,000, 10,000, even 1,000. And it's a very small fraction of the sandbox that makes up just our island universe. And the sheer weight of numbers alone makes it an interesting question. So, but he was the one who initially framed how we think about and go about addressing the question of and problem of searching for life elsewhere in the universe. So that was Frank Drake and the famous Drake equation. OSIRIS-REx looks like it's on its way back. This is a probe that made contact with asteroid Bennu, and I believe it took samples, and they will drop them off in the Utah desert a year from now, actually a year from our planned Village Creek Star Party, September the 24th, 2023. And then those samples will be curated to NASA's Astromaterials and Exploration Science Directorate, and we'll actually be able to study asteroids. So we'll keep an eye on that over the next year or so. And remembering Donald Machholz. I was not familiar with this individual, but it looks like he was a comet hunter and also one of the inventors of the Messier Marathon that we're very fond of in the spring months. He actually completed the Messier Marathon 50 times himself and was also a columnist with Earth Sky and Astronomy, had an astronomy podcast called Looking Up with Don. And 12 comets bear his name. The first one he discovered in 1978 and the final one in 2018. So another contributor to the realm of amateur astronomy and professional astronomy has passed. So we remember him. Okay, fall elections are coming up. So every year around this time, we select a nominating committee to solicit interest among our members for serving on the board. We do have a couple of spots opening up this year, and all officer positions are once again in play. So if you are a paying member and you want a shot at any of these positions, including president, they're open, and you can raise your hand and volunteer to serve. If there are multiple people who are interested in running for a position, we'll hold an election. That will be at our fall or at our November meeting. And then the nominations will be closed officially after our November meeting. And then if there is a vote, we'll do that in December. Otherwise, it will be vote by acclamation. So, which is what it's been the last few years. Correct me if I'm wrong on this, Rick. But now's the time to be thinking about it. And we got a couple months. And again, we got a couple positions opening up. A few people are looking to step off the board and take a break. And again, every position is open. So you want to do VP of programs or treasurer, or president or secretary. Those positions are all in play. So be thinking about it, and someone may be contacting you soon to see if you are in fact interested in serving on the board for 2023.
And I can tell you that as current treasurer, we have it in our budget to double all the board members' salaries next year. So keep that in mind.
That would be zero.
2 times 0, what is that?
2 times 0, whatever that is. So I think 1 is the identity element. What is 0? There's a formal definition in math for 0. It's not the identity element. It's something else.
It's just a placeholder.
It's a placeholder. There you go. 0 is an important number, but hey, it's a volunteer army. It's a labor of love or insanity, however you want to look at it. And by the way, for the current board members, I do appreciate everyone stepping up and making a contribution this year. I mean, can't do this alone, of course. So everyone who has stepped up this year, as well as the people on the outreach committee and other positions, people bringing our telescopes out to our observing sessions, makes a tremendous difference. So again, thank everybody for their contributions this year. All right, we had another great session. Okay session, I should say, at Burton's. We had 2 observing sessions on August the 27th. One at Mosh that I heard was rained or clouded out, and then Burton's surprisingly was clear, although we had quite a bit of dew, but we still had a decent night, pretty good seeing, and yeah, we had some good observing there before we were dewed up. And want to give a shout out to Steve Wright for capturing this image of the Veil Nebula. Very nice. And speaking of astrophotography, for those of you who are interested in learning more about this, we have a focus group that meets about the middle of the month. Next Wednesday is our next meeting. And again, we'll send a notice out regarding this as well. And you can check out videos of our previous meetings on our YouTube channel if you want to get up to speed on that. But basically the idea here is to get teachers and learners together. So it doesn't matter what your level of experience is, just jump in, tag along. If you have questions, you can reach out and get those answered and get some guidance from people who have been doing this for a while, are experts in the field. And it's just another opportunity for people to engage and interact. If this is something you're interested in and are very passionate about, and get some really quality mentoring. So people have been doing this for a long time. So, and I also want to make you aware that there's a form on our website for the astrophotography group. I just learned of this myself. So you can click on that link there, astrophotography focus, and just fill out your details, including some of the questions you have and how you heard about us. Rick, were you aware of this?
I was, Jeremy.
Okay.
And we do most of our communication as a subgroup of the Memphis Astronomical Society via Slack. So a lot of information passed back and forth in Slack. So if you're even remotely interested, get signed up. If you want to subscribe to get on this Slack, it's kind of like a instant messaging system of sorts, but there's a lot of good information out there. So
yeah,
come on in, dive in. The water's fine.
The water's fine, exactly. So you can leave your details on this form, and you can reach out to Rick or one of the members in the group, and they can send you a link to that Slack channel. It's probably best to just jump in on our next meeting if you're interested. That's September the 14th. We do this once a month, again, right around the time of the full moon, and then they can give you the link to the Slack channel, and then that's a great way to get involved. So if astrophotography is something you're interested in, or you want to learn more about it, this is a great opportunity for you. All right. And with that, we're just going to jump right into tonight's program. Of course, many of you have seen the images, the spectacular images that the James Webb has captured, releasing their first set about 2 months ago on July the 12th. And data is continuing to come in almost every day. This is quite an ambitious project. And speaking of NASA, this is one of the projects that's gone flawlessly. Took some time, but the launch was great. The deployment, the unfolding of the telescope, the positioning, and then the first images. So you look back at where we were a little less than a year ago prior to the launch, and then where we are today, to have a presentation like this tonight is really exciting. So with that, I'm just going to turn it over. I'm very excited to hear from Dr. Ann Viano, who's an active board member and also active in our outreach committee or outreach team. And she's an associate and Lester Crain professor in the Department of Physics at Rhodes College. And I'm going to turn it over to you, Ann. Thank you very much. Take it away.
Great. I need you to stop sharing your screen so I can switch over. Thank you. Okay, well, thanks for your patience with the little technical glitch. The James Webb data is many megabytes, and I guess I just had too many images in this presentation, but I think we've solved the problem. So I'm excited to talk to you about this amazing new telescope, and I hope you've had a minute or two to stare at this beautiful image of the Tarantula Nebula. It was just released earlier this week, and I kind of prepared this talk before this week, so I had to put this image somewhere. So I thought I'd put it right at the beginning. But I want to talk about the science that the James Webb Telescope will be working on, because we've seen the beautiful images, and I know a lot of folks in this group have been asking me, well, what is it going to contribute to astronomy, and what's the science it's going to do? So we'll talk about that. But in order to understand that, we have to learn a little bit of cosmology, a little bit about galaxies, and then how do we do chemistry in space. And then we'll talk about the Webb's instrumentation. I know we have a lot of people who are really into telescope instrumentation and cameras here, so I thought you'd be interested in how the Webb does make these beautiful pictures. We'll look a little bit at some other space telescopes quickly, and then we'll just start looking at some of the amazing data that's been coming from the James Webb. So I first want to talk a little bit about the wavelengths of light. So most people here understand that the light we see is just one part of a much larger spectrum of electromagnetic radiation. And up here at the top, I have images of something you probably recognize. I know some people here will recognize this, but these are images of an object in different wavelength regions of the electromagnetic spectrum. So if you looked at this object with a visible light telescope, you would see this. With an infrared telescope, it looks very different. With a radio telescope, it's pretty hot in the middle. If we go to other wavelengths of light going shorter, we have an ultraviolet image, an X-ray image, which is really interesting looking, and then we have gamma ray image. And I know some of you know what this is. This is supposed to come up. Yes, there it is. This is the Crab Nebula. So this is a supernova remnant imaged in different wavelengths of electromagnetic radiation. And then on the bottom here, it shows you how do we get those different types of radiation. Some of them make it all the way to the surface of the Earth. So there is an optical window, and visible light, which we can detect with our eyes, makes it all the way to the surface of the Earth. A little bit of ultraviolet does, and a little bit of infrared does. And then down in the radio region, we do have radio wavelengths that can make it to the surface of the Earth. Most of the other wavelengths are blocked by the Earth's atmosphere. So if we want to take an X-ray image, we need an X-ray telescope. If we want to take a gamma ray image, we need a space telescope. We need to get out of the Earth's atmosphere in order to image in these ranges of the electromagnetic spectrum. So we have a lot of visible light telescopes on Earth, but it doesn't hurt to get them outside the atmosphere as well for increased resolution. So the James Webb has 4 scientific themes that it plans to address over its mission. And the first 2 relate to a little bit of cosmology and how the universe began. The first one is to look for the earliest stars that formed and to see how those stars evolved and maybe helped give rise to the evolution of the first galaxies. The second one then relates to how did those galaxies come together and how did those galaxies evolve? Were they the same as the ones we see now, or were they different? The last 2 goals relate to stars and planets. So how did stars form? And as stars form, so do their planetary systems. And then also, how do we look for life in a planetary system or on a particular planet? So I have an image of the James Webb back here. I think that's the only image maybe in this presentation. There might be a few other ones, but I'm guessing we've all seen tons of images of it because We watched it launch, we watched it being built. So I won't go too far into that. But the first goal, I said, relates to the early universe. And technically, it's called looking for information from the end of the dark ages, which sounds very medieval, but looking for a first light of a certain period of the evolution of the universe. So the questions here are, how did the very first stars form? Were they like the stars that we see forming today, or were they different? Some people think they were much more massive than the stars that form today. And those stars evolved and went supernova, especially if they were massive stars, they would explode in a supernova. Well, how did that affect the next generation of stars? And when you get enough stars, you start to get a galaxy forming. So we need to know, where did the first stars form and how did they form, and was it different than star formation today? So when we think of the evolution of the universe, we sometimes see this cosmological cone. It's a little bit hard to understand the first time you see it, but running along the bottom is just the arrow of time. Literally here, it's an arrow of time. But about 14 billion years ago, there was the Big Bang. And then we have sort of different periods of time where different things happened in the universe. And here we are 5 billion years ago. That's when the sun and its planetary system formed. And this first goal of the James Webb refers to looking at this region right after this end of the dark ages, which sounds kind of spooky. So I need to explain that to you. So the cone is now flipped around. So time is now starting at the Big Bang on the left and expanding to the right. And for the first about 300,000 years after the Big Bang, that was this section here up until this interesting image here. And that is what we describe with the so-called Big Bang theory. That explains the first 300,000 years of the evolution of the universe. And in this 300,000 years, a lot of different things happened. First, we had a very brief period of time where the universe was so hot and so dense that it was just matter and antimatter transforming into energy, and the energy transforming back into matter. It was really a chaotic, crazy place of matter and energy. But then as the universe started cooling and expanding, you started to have particles that could persist. So particles like electrons and quarks could actually stick around. And then as the universe continued to expand, it continues to cool. So then you can have quarks starting to get together. And when you get 3 quarks together, they can form a nucleon, which is a proton or a neutron. So we call this the nucleon era. And it's just a fraction of a second that these eras last. It continues to cool, it continues to expand. And that's why this cone is getting bigger, because the universe is expanding from this infinitesimally dense, an infinitely dense region. It expands, and as it expands, it cools. And so you can have things starting to stick together. So after you can form protons and neutrons, these nucleons, it gets cool enough that those nucleons can stick together and start to make atomic nuclei. And this period of time lasted long enough to make hydrogen nuclei, which is just 1 proton, helium nuclei, which is 2 protons and 2 neutrons, and maybe a little bit of lithium. It didn't last long enough for any more nuclei to form. And we can actually predict the ratio of hydrogen to helium that formed with our Big Bang theory, and it exactly matches what we observe today. So that's one of the pieces of evidence for the Big Bang theory, is the ratio of hydrogen to helium is exactly what the Big Bang theory predicts. Now, once you have nuclei, the universe continues to cool, and then those nuclei can trap electrons, and now you've got atoms. And that is supposedly happened about when the universe was 300,000 years old. So all of that was in this first 300,000 years. And at that time, the temperature of this young universe was about 3,000 degrees Kelvin. And when you account for the expansion of the universe, this is exactly the radiation that was found by the COBE satellite in 2001, I think. And there was a Nobel Prize right there, but we actually observed the radiation from this moment at the end of the formation of atoms era of the Big Bang, and this was evidence for the Big Bang as well. Since that time has marched on, and after we had atoms, the universe is now transparent because radiation can pass through atoms. It can't pass through a soup of particles or a soup of nuclei, but once you have atoms, radiation can pass through. So now the universe is transparent, and there was this region of time where you just had some atoms hanging out, and the universe was getting cooler, and that's what's referred to as the Dark Ages. Once those atoms are kind of hanging out in the universe, sometimes they get close together. And when they get close together, gravity takes over, and this is where the James Webb can start to observe. Gravity takes over, these hydrogen atoms get reionized, and they could start to get together and start to form stars. So the James Webb will allow us to look all the way back to the end of these dark ages, right when things got really interesting. We had all these atoms floating around, and the atoms could start to get together. And what do atoms do when they get together in the universe? They're going to start to form stars. So hopefully we'll be able to see the very first stars that have formed. There's a problem, though. The problem is that the universe has been expanding ever since those first atoms formed, ever since the Big Bang, really. But it's been a long time since those first atoms formed, about 13.7 billion years. And in that time, the universe has been stretching and expanding, and that physically changes the wavelengths of light that we would see when we would look at those early atoms. And so this little video shows you how the stretching of space-time stretches the wavelength of light from a distant object. So here we are on Earth. Here's a galaxy that we would like to observe. Maybe it's the first galaxy that ever formed, and we want to observe that light. Now, a galaxy itself will emit all wavelengths of visible light, so we're looking at some blue wavelengths. The problem, there should be a way to play this. Hello. Okay, my videos won't play, but we're just going to go on. The problem is that as the universe stretched, this fabric, this grid that this galaxy is sitting on is physically stretched, and that's going to stretch this wavelength and change it from blue to a larger wavelength like red. And I'm not sure why I can't get it to play. Nope, not going to play. I'm not going to argue with it. So we're just going to go on. So what would happen is that this blue galaxy would get pulled away from the Earth as the fabric of space-time stretches, and the wavelength of light that it's emitting shifts to a longer wavelength.
Hey, Ann, I think the play button was in the lower left.
That's forward and backwards.
Oh, forward and backwards. Okay.
Yeah. Usually there's a big arrow that shows up on the screen, but with all the problems I've had, I'm not going to worry about it. So we're just going to move forward. So a galaxy that may be formed right at the beginning or early years of the universe would be emitting lots of visible light. But since the universe has been expanding for 13.7 billion years, the wavelengths of light that it emits will have shifted into the infrared. And this is why the James Webb Telescope has to be an infrared telescope, because the light we're looking for has been traveling so long in the universe that the universe has shifted it to these longer wavelengths. Just like the radiation from the end of the Big Bang Theory, that 300,000 years, that was even further than the James Webb will see. It had shifted all the way into the microwave. These early galaxies and early stars will have shifted into the infrared part of the spectrum. So if we go back to our little picture, we can see here now I've labeled here, we saw the microwave COBE data, which had been shifted from visible type wavelengths all the way into the microwave at about 14 billion years. Then about 13.5 billion years ago, we start to have the formation of stars, those first stars forming. This light will be shifted into the infrared, as will the light of the very first supernova from these first stars and the light from these very first galaxies. They will be shifted into the infrared, and that's where the James Webb is going to look and try to see this distant light. All right.
And if you have another video, you might try the keys Alt and P.
Alt. Nope.
Okay.
I'm not going to mess with it after what we've gone through already. It's okay. I can describe the video, hopefully. So the first goal we said is going to look for the first stars. The second goal is to try and understand how the very first galaxies in the universe developed. The first stars may have been different, and so maybe those galaxies were very different. So how did the first galaxies form? How did we end up with all the different types of galaxies we see today? So this is a Hubble montage of different galaxies, and they're beautiful to look at. And as you look at them, these are all spiral, but there are also elliptical galaxies that we see today. Here's a beautiful spiral galaxy, not unlike our Milky Way. And as you look at these galaxies, you notice there's a lot of structure in these galaxies. There's, beautiful detailed arms and swirls and wall-like structures. So they're very organized. Most of this information came from the Hubble Ultra Deep Field, which, believe it or not, was in 2003. So it hasn't even been 20 years since we started noticing that galaxies far away looked different. These are galaxies that are nearby. They're very organized. They're very beautiful. They come in different types. We understand them pretty well. But with the Hubble Deep Field, we were able to start looking at galaxies farther and farther away. And we noticed that those galaxies look different. So the farther away you look, the further back in time you see, so the younger the object is. So some of these early galaxies that formed in the universe don't look like the galaxies we see today. There are these clumpy little tadpole galaxies that came from the Hubble Ultra Deep Field. They don't look like spiral galaxies today. They don't look like elliptical galaxies. There were clumpy chain galaxies where there is some organization, but you also see these like blobs of material. There are clumpy spiral galaxies, so they're not the beautiful organized spiral arms that we see today. They seem kind of clumpy in some spots and then less clumpy in other parts. And then there were some that were kind of in between. They call them clumpy cluster galaxies, where it's just kind of random clumps that seem sort of organized, but not in a beautiful way. They're just kind of next to each other in space. So the question that James Webb wants to answer is, what's going on with these galaxies? Can we get better pictures of these early galaxies? And can we maybe get more information than just a picture and see what's going on and how these early galaxies formed? So when you look at pictures of galaxies, there's often a number here that's called the redshift number, and that relates to the distance to the galaxy. So if you see this, you're usually seeing redshifts between 0 would be right next to us, up to about 2. That's a very distant galaxy, about 15.4 billion light years away, which is older than the universe, so or further than the beginning of the universe. So we would probably never see a galaxy of redshift 2, but a redshift of 1 tells you that that's a galaxy whose light has been traveling to reach us for 10 billion years. So a 10 billion light year away galaxy. So another way that we can use the universe to our advantage, and James Webb has already demonstrated that it can do this pretty successfully, is it can use gravity to see things that are very, very faint and very far away. And this is the method of gravitational lensing. And basically it uses a clump of mass as a lens and the gravitational interaction with that mass as a lens to bend light and to magnify the light. So here's an image that you may have seen before where we have some random galaxy cluster, and a cluster of galaxies is a lot of mass. It's a very massive object. So the gravitational field around this galaxy is very, very large. And then we have a very distant galaxy far behind this massive cluster. The light coming from this very distant galaxy is physically bent by the gravity of this large cluster, and it can be bent in such a way that it almost acts like a telescope, and it brings the light to a nice focus and concentrates the light from that distant galaxy. So gravitational lensing can allow the Hubble to see really, really far away if we can get, things in just the right place. And this is an image from, it's like an inset image from the Hubble, the James Webb's Deep Field that was released by President Biden in the big press conference. And we were already able to see these lensing artifacts, these rings and arcs are evidence that we're seeing lensed light from distant objects. There's a large galaxy cluster that's sort of close to us, and then things from behind that cluster are being lensed, and the fact that we can get light from them is amazing. They may not look like a distant galaxy, although some in the image do. They just look like a smear, but James Webb has tools that can take that smear and learn from it. It has spectroscopic tools where we can actually get information about the composition of the galaxy. So this gravitational lensing is going to become important, and it already has been with the James Webb. So the third goal is all about stars and planetary systems. And in order to see stars forming, you have to look where stars form. And they form wherever there's lots of stuff, lots of material for stars to form. So they form in these clouds of dust and gas. So lots of hydrogen available to make new stars and all kinds of other materials in there. And that's really hard to see through unless you have the right kind of telescope. So here we have an image of the Crain Nebula, and this was one of the James Webb's first image. This is on the left, this is a Hubble image of the region. On the right is the James Webb image. Because the James Webb is focused with, is using only infrared light, it allows us to penetrate that dust. And I'll explain why infrared light is useful for this. The Hubble is mostly a visible light telescope. It can do some infrared imaging, but not as wide of a range of infrared as the James Webb. If you like these comparison images, you can actually slide this slider back and forth, go to this website, and you can do this for about 5 of the James Webb images. You can compare Hubble to James Webb and go back and forth and just marvel at technology. So why is infrared light better for penetrating dust? Probably something you're really familiar with. So it turns out that light can pass through dust if it's the right wavelength. So here we have some sized dust grains here in kind of yellow. And if these dust grains are, say, the size of the wavelength of green light, then wavelengths that are shorter than green cannot pass through. But wavelengths that are longer than green, like red light, can pass through. So the red light would pass through, but the blue light would get scattered in all directions. And you've probably observed this, you just didn't know it, when you observe the sunrise or the sunset. So if we've got the sun over here on the left, it turns out that the particles in the Earth's atmosphere, well, they're about the size of the wavelength of green light. So longer wavelengths can pass through the Earth's atmosphere, but shorter wavelengths like blue scatter in all directions. So if you're over here observing, say, a sunrise, you look up at the sky, you see mostly red because the blue light is getting bounced away from the Earth. Same phenomena here at sunset. The red light is passing through, the blue light is getting scattered back in all directions, so your sunset is a beautiful red color. So our Earth's atmosphere is kind of funny that way, that it kind of splits blue and red. It seems to be right in the middle of the visible spectrum. But in outer space, the dust covers the range of the entire visible light spectrum. So the only wavelengths that can pass through interstellar dust are longer than the visible light. So longer than red. And what's longer than red? It's infrared. So in order for us to see light coming through the interstellar dust, we look for infrared light because it will penetrate. So here we have an image. These were those pillars of creation. These are both from Hubble, but this is a visible light image. And you can see these beautiful pillars, and you can see, stars forming at the tips and points. But then in the infrared, the dust pretty much disappears because the infrared light can pass through that dust, and it allows us to see what's going on inside these pillars. So we can see stars forming inside these pillars of creation. So it's really an amazing feat that dust works this way, and we can penetrate that dust just by choosing the right wavelength to detect. Now, the last goal refers to planetary systems, and in particular, looking for life on planets or life-bearing planetary systems. So the questions are things like, what's the composition of the atmosphere of a planet, and does that composition contain anything that might give indications of life? So this is just a graph of the number of extrasolar planets discovered by year, and it's cumulative. And so as of today, we are over 5,000 extrasolar planets. So it's not just Earth. There are 5,000 other planets out there that we know of. There are probably 10 or 100 times more than that, or maybe 1,000 or 1,000,000,000. And then the colors in these bars just relate to the way that this extrasolar planet was detected. And you see that the green really takes off here, and a lot of these planets were discovered by this transit method. That was the Kepler telescope, which has now been retired, so it's no longer operating. But when Kepler turned on in the 2007 or so, we started, this number just increased rapidly. So we're now over 5,000 planets. So what do you have to do to find out if there are markers for life in an extrasolar planetary system? Well, you have to find the planet, and the James Webb is capable of direct imaging of planets. In fact, that was just recently announced. It could also use the transit method, and it has already successfully seen the light of a star dim as the planet passed in front of it. And then you want to analyze the atmosphere of that planet or analyze the planet itself. So some way you need to be able to get some chemical data. What's in the atmosphere of that planet? And so the James Webb can do spectroscopy on the atmosphere of the planet. Okay, I'm looking at the chat here. I'm seeing a few things, but it doesn't look like any burning questions. So I need to tell you a little bit about spectroscopy because this is God's greatest gift to astronomy. So spectroscopy is basically how physicists do chemistry, or how astronomers do chemistry in outer space. And you've all experienced this. If you take some light and you pass it through a glass prism, that light will spread out and you'll see a beautiful rainbow. And you can break up, you can see the different wavelengths of light that were contained in the original white light. They got spread out. So you can see the red, you can see the yellow, the blue, the green. You can see all those different wavelengths. And spectroscopy is attributed to Sir Isaac Newton. And the story is that he had a hole in his dormitory at Cambridge, and he would allow the sunlight to come in the hole in the wall, and he would shine it through a prism, and he started the science of spectroscopy that way. I don't know, this looks like a really fancy dorm room to me. It looks like a laboratory, but it works. So in astronomy, we can do spectroscopy on light from anything. So we can look at the core of a star. We can take that light, we pass it through basically a prism, although in science we use something a little fancier called a diffraction grating, but it has the same effect. And then we can split that light up into its wavelengths. And this got cut off a little bit, I'm sorry, but if we do that to the core of a star, the spectrum is smooth and it contains all the wavelengths. It's what we call a black body spectrum. It's continuous and contains every single wavelength. If instead the light from that core, the core of the star, passes through some gas like the atmosphere of a star, well, this gas is full of atoms, and atoms love to suck up light. So these atoms will suck up a couple of wavelengths, and then you'll see missing wavelengths in the spectrum. So we can then look at these missing wavelengths, we can measure them, and we can figure out which atoms they come from. So we're able to determine the composition of this gas. So we've been doing this for a long time. Spectroscopy in terms of astronomy really got going in the latter half of the 1800s with the Harvard astronomy, the Harvard Observatory, and they were looking at spectroscopy for stars. So the light was coming from the star, it passed through the atmosphere of the star, and then it had all those missing wavelengths. And those spectral lines are kind of like fingerprints. And the Harvard astronomers, the women of the Harvard Observatory, categorized the stars based on the pattern of those missing lines. And that's how we got the catalog of stars that we know today, the O-type stars, the G-type stars, the M-type stars. They had very distinct fingerprints. And that relates to what atoms are contained in the gas that light passed through. So this work was amazing work, and it allowed us to classify stars, which then helped us understand the main sequence, which helped us understand how stars evolve. It also helped us discover variable stars, which then let Hubble start to measure distances to things beyond the Milky Way. So this was really, really important, and it's very difficult work. Here's just a tiny portion of the spectrum of light from our own sun. You see all these missing lines, these absorption lines. There are thousands of them. And compare that to the star Vega, it's very different. Vega has this big gap, and it has a different pattern of lines. Each one of those lines is telling us about the composition of the gas in the atmosphere of that star. And it can tell us exactly what the atoms are bonded to, if it's hydrogen bonded to oxygen or carbon and two oxygens. Each one of those lines can be categorized and can tell us exactly what's going on composition-wise in the atmosphere of that star. Now, the James Webb could do that. It could take light from a star, it could pass it through its instrument, and it can attain the spectrum, and then it could measure it. It could turn it into a graph, just how much light at each wavelength. And so you can get a quantitative measurement. But you could also do it this way. You could take light from a star and then let that light pass through the atmosphere of a planet orbiting that star. Then your spectrum would give you information about the atmosphere of that planet. Each one of these dips corresponds to some kind of molecule or atom in the atmosphere of the planet. So this is how the James Webb is going to look for evidence for life-related molecules and atoms in the atmosphere of a planet. And it's already succeeded. That was one of the first 5 images released. Oh yeah, so here it is actually, WASP 96b. This was one that was in the first release from James Webb. This is basically the spectrum here, and it has a lot of data points, and they've identified H2O molecules in the atmosphere. And a more recent one, in just the last week or so, identified carbon dioxide in the atmosphere of an extrasolar planet. So a lot of exciting work going there. Oh yeah, Freddie just posted that. He saw the one about carbon dioxide in a planet. So the goals of the James Webb are basically driving the requirements for the telescope. It needs to be an infrared telescope because we want to get that longer wavelength light because it can pass through dust, and because that's what the light from the earliest stars and galaxies has been shifted to from this stretching of space-time. An infrared telescope means it has to be a cold telescope because Earth and Earth's environments give off infrared light. So we have to get the telescope away from Earth. So that's part 2. We do want a telescope with very good resolution because these distant stars and trying to see a planet, you really need good resolution. And in order to have good resolution, you need a really big telescope. Resolution goes with the diameter of the telescope. So the bigger the diameter, the better the resolution. But resolution also goes as the inverse of the wavelength. So the bigger the wavelength, the bigger the telescope you need to maintain resolution. So this thing has to be big. And then we also need a way to determine chemical information. So the James Webb needs to have some onboard spectroscopy equipment or a spectrometer. It actually has 2. So let's just look quickly at space telescopes through the years. These are telescopes, some telescopes. There have been more than that are on this slide, and it also shows the wavelength range. So if we start over here with gamma ray telescopes, there are a few that are up there. The Fermi telescope is up there looking for gamma ray bursts. We have Chandra, the X-ray telescope, a couple of other high energy or short wavelength telescopes. Kepler has been retired, but it was a telescope looking for planetary transits. We have the Hubble, which is in the visible range, and it does do a little bit of infrared and a little bit of ultraviolet, but mostly visible. The Spitzer Space Telescope was also in the infrared, but it has been retired. We had the Herschel, but it's now retired. The Planck telescope, which was in the microwave, is now retired, and another retired telescope. We do have a telescope that flies around in an airplane, so it never retires because you can upgrade it when it lands. And then on Earth, we have a lot of telescopes in the visible range, because remember, visible light can make it to the surface of the Earth. We have some radio telescopes because radio waves can also make it to the surface through the Earth's atmosphere. And then this one over here is a gamma ray telescope, but it's on the surface of the Earth because it has a very special mission. It's looking for cosmic rays that do get through the Earth's atmosphere. But most of these high energy, short wavelength radiation does not get down to the surface. So where's James Webb? It's going to be right here. It's sort of between Hubble and Spitzer in that it looks at the near infrared and the mid infrared. So it does overlap a little with Hubble, but it can do a much better job in the infrared, and Spitzer is now retired. So it fills a nice niche. So over here we see an image in the infrared taken by the Spitzer Space Telescope, and this is showing you the wavelength. That's 8 microns, which is 10 to the minus 6 meters. And then this is the same stars, the same 4 stars taken by Webb. So Spitzer was a great telescope. It worked in the infrared, but James Webb is better. It has much more resolution, and you can see that. Just look at the resolution of these stars and the detail in this image, which is roughly at the exact same wavelength that the Spitzer image was. So it's a better telescope because it's bigger. So Spitzer was a tiny little infrared telescope with a diameter of maybe 3 feet. The Hubble is a nice visible light telescope. The diameter of the mirror is about 8 feet. And here's the James Webb, 22 feet. So bigger diameter means better resolution. So the Webb is going to be much better in terms of seeing and distinguishing 2 stars that are really close together than either one of these telescopes. So here's just if you need to, I'm not really good at visualizing 20 feet. So here's a human, and here's the Hubble's mirror, and here's the James Webb's complex composite mirror. And this is an actual life-size model of the James Webb that used to go around the country when they were trying to drum up interest, and it would show up at different physics meetings. I think it showed up in Atlanta when I was at an APS meeting, and it's shown up at various places, but these are people, so you get an idea of the size of this telescope. Okay, so just a little bit more comparison of wavelengths. Here's the Hubble telescope. It was mostly in the visible, but I said a little infrared, a little infrared, a little ultraviolet. The James Webb is going to be the near infrared and the mid infrared, and the Spitzer was mid infrared to far infrared. So there's a little bit of overlap, but these telescopes were designed to look at specific regions of the electromagnetic spectrum or just specific types of light. Okay, so how does the James Webb accomplish these lofty goals, right? It seems really hard, and it is a really difficult project. So this is something you've probably already seen, but we have the main mirror, the secondary mirror. The light then comes through the center in sort of a Cassegrain model telescope, and then the business end is behind the main mirror. All of the scientific equipment is packed behind the main mirror. And then this beautiful tennis court sized shield is simply to keep light from the sun from heating up the telescope. So the main parts of the scientific package are a couple of cameras. We have the near infrared camera, and then we have the mid-infrared instrument, which contains a camera. And it's pretty clear, the name tells you near infrared means that this camera can make images from light in the near infrared part of the spectrum. The mid-infrared would be a little bit longer wavelengths, and the MIRI instrument has a camera, so it can make images in that part of the spectrum. It has a dedicated spectrograph for the near infrared part of the spectrum called near spec. And then it has the fourth part, which I'm not really going to talk about because this is solely for guidance and for pointing of the telescope. So it's just a guidance sensor. There's actually another spectrograph in here and an imager, but it's used for guiding the telescope and keeping it pointed at the object. And you can see that this is a very international type of project. We've got University of Arizona, NASA Goddard, but also the European Space Agency and the Canadian Space Agency. So I know a lot of my astrophotography friends are interested in these sensors. So this is a picture of the NIRCam detector, and there are actually 4 of them put together. And this is the range of wavelengths that it detects. So these are micrometers, 10 to the minus 6 meters. And the absorber in this detector is a mercury cadmium telluride. And there are about 4 million pixels in each quadrant of this NIRCam detector. The MIRI detector is a arsenic doped silicon, and so these are the little bit longer wavelengths of the mid infrared, and it's a good size detector, 1,000 pixels in each dimension. So how is this packed together? It's all kind of stuck behind the main mirror, and this is a picture of just the near spectrometer. So the spectrometer is a main chunk of this scientific package. Near spec is the spectrometer for the near infrared wavelengths, and it's this very complicated beast with many, many parts. The light kind of comes in from the left, and it bounces around through various parts, through the gratings, and eventually into a camera where you can actually get a picture of the spectrum, and then that data is sent down to Earth. But you'll see there's a filter wheel here so that you can look at very specific parts of the spectrum. And then right here, there's this thing called micro shutter assembly. This is an amazing device, and this is an expansion of that shutter assembly. There are 250,000 tiny little shutters that can be individually opened and closed to allow light from only 1 pixel of the image into the spectrometer. And this is actually an electron microscope. The size of these shutters are about the size of a human hair. So 100 microns in 1 dimension, that's about the width of a human hair. So these tiny little shutters that can be individually controlled so that you can then let light from just one part of the image into your spectrograph. And this is just something with actual humans in it, so you can get a size of the spectrometer. And you can see here is, oh, it's hard to see. This is the camera, this is the grating wheel, and here's the filter wheel over here, and the micro shutter assembly would be this section here. So speaking of filter wheels, both of the cameras and the spectrometer have a variety of filters and actually apertures, so they can change the shape of the light that is entering the spectrometer or the camera. For the NIRCam filter wheel, it has short wavelength channels as well as long wavelength channels. So lots and lots of different filters, so it can pick out the narrowest region of the electromagnetic spectrum to get just light from, say, the 1.15 micron region. So this is F115W. That means that it's a filter centered at 1.15 microns, and the bandwidth is not very big. And there are a ton of these different filters, so we can just pick out different regions of the spectrum. Now, MIRI also has a spectrometer on board and also has a filter wheel. And this is an actual picture, not a cartoon, of just the many different filters and apertures that can be used before the light goes into the imager for MIRI or its spectrometer. And it's really a complicated piece of engineering to not only design, but to machine this filter wheel. I think it's a really beautiful filter wheel, and it's probably a priceless kind of filter wheel. So with these filter wheels and the 2 cameras and the spectrometers, we put them all together in the scientific package for James Webb, and then we send the James Webb way out this was another video GIF, but it's not working, but that's okay. This was to show the orbit of the James Webb. So we've got the sun here at the center, Earth, and then the James Webb orbits a point. So it's actually orbiting out of the screen and into the screen in this circular orbit around a point called L2, which is just a point where there's sort of a gravitational stability. So it orbits around, and as the Earth goes around, the James Webb on its loopy-loop orbit follows, going sort of up and down as the Earth goes around, always facing away from the sun and away from the Earth, with that big sun shield facing the Earth and the sun to keep any infrared light from heating up the telescope. Okay, so let's look at some data now, unless this might be a good place to stop and see if there are any questions.
I think I'll save mine for the very end.
Okay, I see someone commenting on the price for 10 billion. But remember, that 10 billion was spread over many, many, many years. So it's a tiny chunk of our national budget every year. Okay, well, if there are no questions, we'll start looking at the data, because I think that's the really exciting part, and it's just going to get better and better as time goes on. So the first goal of the telescope was looking for the first light of these early stars and maybe the earliest galaxies. And I want to start with this Hubble image. This is part of the Hubble Deep Field. And if you look at this little inset that's blown up here, there is an arc due to that gravitational lensing here, but in that lensed light, there was a little dot. That dot is a star, and it is the oldest star ever imaged, which means it's the most distant star ever imaged. It's called Arendelle, and it took the light from this star about 13 billion years to reach us, and it's not particularly bright. So the only way we could see it was by this gravitational lensing, which concentrated the light, and we were able to pick it out of a smeared out arc of light. So this was from Hubble. And then James Webb looked at the same region of space, and Arendelle is right there. You can't really see it. At the tip of that arrow is this smeared out arc of light and an image, a gravitationally lensed image of that oldest star. So the James Webb has already accomplished one of its goals, which is to look at the earliest stars that we can see that formed in the universe. I don't know that they have taken any spectroscopic data of this star yet. I suspect that's probably some scientist's project, and they'll be publishing a paper on it probably pretty soon. But it's really exciting that we are able to image stars that are almost as old as the universe. Not quite, we can't get past the dark ages, but almost as far back as the beginning of the universe. So everyone probably has seen this image. This was the deep field image that came from the James Webb. This was one of the first announcements, but it's a beautiful image. It was taken with the near cam, so it's a near infrared image. And again, this is where we started to see all this gravitational lensing, these smeared out arcs. And this one in particular, it's a smeared out galaxy. It kind of looks like one of those clocks that has been, bent and twisted from a famous artist's painting that I can't remember at the moment. But we've got all this information of all of these different galaxies. Everything in this image that doesn't show these sharp diffraction spikes is a galaxy, or a gravitationally lensed image. Oh, Dolly, thank you. A gravitationally lensed image of a galaxy. So there are just so many galaxies here. And the redshift, the gravitational lensing that we're seeing in this image was caused by this galaxy cluster. These whitish blobs are these galaxies that are about 4 billion light years away, which isn't super far away, but they are causing us to be able to see these gravitationally lensed galaxies, which are behind the cluster, so much further than 4 billion light years away. And so there's a wealth of information hidden in these arcs and images of early galaxies.
I have a question, Ann.
Oh, yes.
Do they know enough about the mass of the galaxies to be able to mathematically reconstruct what those arcs really looked like?
Usually they do. This data is pretty new, so I don't know that they've actually done that yet for this particular image. But yes, you can work backwards from the mass of the cluster and kind of reconstruct what these smeared out galaxies really should look like.
I look forward to that. That'll be cool.
That's a great question. So the way this image was constructed is they used 6 different filters and made a 4-channel image. So they had a blue channel that was light from 2 filters, a green channel that was light from 2 other filters, an orange channel from this particular filter, and a red channel from this filter. So the light, the colors are just the longest wavelengths they measured, they put on the red end, and the shortest ones they put on the blue end, which is a logical way to do it. You wouldn't want to get them out of order, I guess. So this is a great image. It has a wealth of information. Now the James Webb can use its shutters to do spectroscopy on each of these little blips. So remember that little micro shutter array, we can close all of the shutters, but open, say, just this one. And we can take the light from that one galaxy, send it through the spectrometer, and get the spectrum of that one galaxy. And then we can close that shutter and open another shutter and take the light, put it through the spectrometer, and get the spectrum of that particular galaxy. And they're starting to do this with the data coming back. And this just shows you the red is hydrogen lines coming from the galaxies. And these are put in order of redshift, so lowest redshift to highest redshift. And the more that the red lines are shifted to the right, the farther away the galaxy is. And that's the cosmological redshift, this stretching of space-time. And you can also see some of the hydrogen lines in here for these different galaxies. And you can zoom in on these spectra and see just minute lines, and you can fit the lines. This is what one of my colleagues does. He's already gotten data from his galaxy, but he told me I couldn't show any because they just submitted the paper on it. So I can't show his data, but they were looking at a very young galaxy, a quasar, and they were looking at the spectrum from different parts of the galaxy. So the core of the galaxy versus the edge of the galaxy. So this micro shutter array allows you to take this amazing image and get chemical information from any one of the galaxies. It's absolutely incredible. Okay, this is an image that I just think is beautiful, and it's a combination image. So this is the Cartwheel galaxy, which is about 500 million light years away, which is relatively close, but we want to practice with the James Webb and making really good images, and then we'll go and look for the earliest galaxies. So this is a combination image made from an image from NIRCam, the near infrared, and an image from MIRI, the mid infrared. These images were then combined to produce the final image. So remember with MIRI, these mid infrared, the longer the wavelength, the more we can penetrate and see into the dust. And so this beautiful composite allows you to see a little bit into the dust, into regions where there are new stars forming inside sort of the parts of this galaxy, combined with the beautiful NIRCam image, which gives us more of a look at what the galaxy would look like. This scale bar, if you can't read it, is 100,000 light years. So this is a big galaxy, the Cartwheel galaxy. And to construct this image, again, they used a mixture of filters. So there were 2 filters that were mapped to the blue channel, 1 filter mapped to the green channel, 1 filter mapped to an orange channel, and 2 to the red. And then they took 4 filters and combined that data and mapped it to an orange channel from MIRI. So many channels added together. Some of the channels then have multiple wavelength regions in them. Okay, here's another beautiful set of galaxies. I kind of go overboard on galaxies. So this is Stephan's Quintet, also called Hickson Compact Group 92. But this is an image from NIRCam, and there are a lot of different things going on in this image. This galaxy on the left is actually much closer than the other 4. This one's 40 million light years away. These are more like 290 million light years away. And there are 4 here, this one, and then these 2, and then there's another one down here. When you combine the near infrared with the mid infrared, you get this image. And now you can start to see what's going on behind the dust that NIRCam can't penetrate because it's looking at short wavelengths. Now we can start to see these huge wall structures. It turns out these are shock waves because these 2 galaxies are in the process of colliding, which is a very chaotic, cataclysmic event that will cause shock waves to ripple through, which will in turn cause more stars to form. So this is a very exciting active region of space. I see we have a question here. How has the micrometeoroid damage impacted observations and can it be corrected? As far as I've read, and I'm not an expert in this, but there really hasn't been any damage. I know that it was a big news story that, oh my gosh, it got hit by a micrometeoroid, but they've planned for that. They know it's going to happen out there. So it's not a problem as far as I've heard.
Can both images or can both cameras be operated at the same time?
Yes, I would think the way that it's designed, I think you could send the light to any one of the scientific instruments. I think I do remember seeing there's like a splitter, so you could probably split it. I doubt that they would do that though, just because it would decrease the quality of the image. But maybe if they find something really excited and they need to do it in a hurry. This telescope is so good that it doesn't have to expose for very long to get enough data to make a beautiful image. So it wouldn't be hard to switch from one to the other. It's not like you're using up someone's time. But that's a good question. Oh, here we are. So here's the same image. This is the Stevens quintet here. And again, they're going to use the spectrometers to learn about these galaxies. So we said this is a really exciting set of galaxies. They're interacting with one another. New stars are forming. So the MIRCam spectroscopy or spectrometer can take an image of a galaxy, take that light at different wavelengths, and you can get a picture then through these different filters. This is a picture of the molecular hydrogen, a picture of the atomic hydrogen, a picture of iron, a picture of atomic hydrogen at a different set of wavelengths. And then you can use the shutter array in the near spec to take spectra of individual parts of one of these galaxies. So here again, we get that chemical information from the center of the galaxy where there's probably an active black hole, and then from away from the center of the galaxy. And the 2 spectra are very different. So there are different things going on at the center of the galaxy than far away from the center of the galaxy. And that's going to help astronomers learn how these galaxies evolve and change with time, which is really an open area in astronomy. How galaxies form and evolve is sort of a big mystery. Hubble had some ideas and then we thought Hubble was wrong, and now some people are thinking, well, maybe Hubble is right. So I don't know which way the pendulum's going to swing in the next 20 years, but the James Webb is going to help us figure it out. Okay, I'm sure we've all seen this. It probably is now your phone background image or something, because it's a beautiful image of the Carina Nebula. And this relates to goal number 3 of the telescope, which how are stars forming and how are their planetary systems forming? So to look for stars, you have to go where they are born, and you have to go to dusty regions of the universe. So this is the Carina Nebula, just full of material where to make new stars. And here again, you can see this is I think this is a NIRCam image. I thought it said on here, oh yeah, NIRCam. So these are the near infrared wavelengths. And again, you can see which filters were mapped to different channels in different colors in this image. But it's a very beautiful image. We see lots and lots of stars. We see like these, it looks like steam, but these are ions. So a flow of ions coming out of this cloud of dust and gas and going back towards where the young stars are forming, that are then blowing all this gas and dust. And then we've got new stars forming in the dust and gas. It's just so much going on in this image. But this is a beautiful NIRCam image. And if we take, I want you to concentrate on just this section here, because now we're going to take a picture of this with the MIRI, the mid-infrared. And this is what the MIRI image looks like. The colors are different. This is actually a combo image where we've added the MIRI data. So back, it's a beautiful image, but it seems like you can't really see into the dust. But when we add the longer wavelengths, the dust disappears and we can see all of these new stars forming in this cloud because we're using those longer wavelengths, the MIRCam. Just a beautiful image. Okay, goal number 3, still looking for planets. James Webb was just able to take an image of an extrasolar planet. So a direct image of a planet orbiting another star. It's really hard to do because the stars are so bright that you can't see the planets orbiting. But James Webb was able to use an eclipsing disk to block the light from the star and then image the planet. So this is just the image in 4 different wavelength regions. The star is actually blocked by a disk just placed in front of the camera, and then you actually can see the planet here in these different images. So this is planet HIP 65426b, and it's a large planet, 12 times the mass of Jupiter, so a mega Jupiter. And we estimate from spectra from the star that it is orbiting, it's about 17 million years old. So this is a relatively young planet. Remember that our planet's about 5 billion years old. So this is probably a new planet forming in a new solar system, maybe around a fairly young star. Just a beautiful image. And then they can use the spectrometer, and this is what we were talking about earlier, to take the spectrum of a planet's light coming through an atmosphere. And this is near spec that got a peak from carbon dioxide in the atmosphere of this planet, WASP 39b, which was this was one of the first day released images. So light from a star passed through the atmosphere of this planet, and we were able to get chemical information about the atmosphere of the planet. It amazes me that we can do this. And here's this beautiful peak showing carbon dioxide. What are the natural processes that generate CO2? Breathing. So when organisms breathe, we exhale carbon dioxide. But there are probably a lot of other ones. I'm not an environmental scientist, so that's the one that comes to mind. Okay, so that's sort of the end of my formal images, but I just wanted to say there are a lot of other images coming out. This Tarantula Nebula, this just came out this week, and here we've got a NIRCam and a MIRI image, so the 2 different wavelength regions, and then you can combine them and make an even more beautiful image. This image of Jupiter was circling around last week. This is a James Webb image of the planet Jupiter using NIRI, and if you compare it to like a Hubble image, the Hubble image would show lots of oranges and reds, but now we're looking at infrared light. This is just the way they mapped it, and the aurora really stand out in this. A couple of tiny moons. I think this diffraction spike here is coming from the moon Io, which is not shown in the image, and you can clearly see that Jupiter really does have rings. A lot of people don't believe me when I tell them that, but I know it really does. And then I found this interesting, although this was not an official James Webb release. It came from an amateur astronomer who went to the website and downloaded the software package to download the data and process it themselves. This is an Einstein ring from a galaxy 12 billion light years away. And the light from this galaxy is bending around another much closer galaxy. So this is gravitational lensing, and we get an almost perfect ring. All of this light in the ring is light from one galaxy that is behind this central galaxy. So Rick was asking, can you reconstruct what the galaxy should look like? And yes, you can. And I hope they do that with this image. but it's not very often that we see a complete ring. It's called an Einstein ring, and this one just came out earlier this week. So I'm going to stop there and see if there are any questions. And I hope you enjoyed some beautiful images and learning a little bit about this telescope.
Okay, thank you very much, Jan. It's an excellent presentation. We'll just go ahead and open it up now. And if you have any questions, you can either enter them in the chat, or if you just want to unmute yourself and go ahead and audibly ask, then we'll just go ahead and do that. What are your thoughts on this image of Jupiter? I mean, it really is a fascinating image. I don't think I've ever seen anything visual of the ring of Jupiter.
I think it's beautiful. I know that we do have images of Jupiter's rings and Uranus and Neptune's rings as well, but I just think the composition of the image is beautiful. The fact that you can see the aurora is really nice. So there is a magnetic field in there, and it's just nice to see that. It's a really interesting image, and it's unlike other images of Jupiter that we've been seeing, our whole lives. So very exciting.
Yeah, it's almost like they were doing this for fun. It doesn't necessarily fall in line with the other four goals of the James Webb, but they're like, well, we have it, so let's take a look at Jupiter and see what it looks like. So I think for me personally, what excites me the most about this is the discoveries that could potentially come from looking back at the cosmic dark ages. And what is that period of time from reionization, when we get the cosmic microwave background? I think it was 370,000 years after the Big Bang to when the first stars form. Do we know what that period of time is? Is it several million years, or how long a period of time is that?
Let me find my little picture of a cone here. Here we go. This one, right?
Right. So the cosmic dark age is basically from when we see the cosmic microwave background. It was mapped by Kobe first in '89, and then 2003 I think was WMAP, and then 13 was Planck. So it's been three different satellites that have mapped it. I believe that's 370,000 years.
Right. This
so
is
going to the first stars, we have this basically this era of matter that hasn't formed structure yet. So like you said, it's dark because their gravity hasn't allowed stars to condense from dust and begin to shine yet. So do we know about what that length of time is?
I don't know off the top of my head, but I know that we're here now at 5 billion years ago, and we need to go back to 13.5 billion years ago. So I don't know exactly what the definitions are, but I would say in the billions of years as opposed to millions of years.
So if we see galaxies or stars that are, say, in that period of time, a couple 100 million years after the Big Bang, then that could potentially change some of our assumptions of and maybe even our model of the Big Bang flow of the universe, if you will. So,
well, the Big Bang theory is this part here, the yellow part, and we understand that pretty well. And there's actually a lot of evidence. That would be a whole nother lecture on evidence for the Big Bang. But it's after that where we're unsure, and that's where the James Webb is concentrating. So it's going to answer questions about formation of stars and galaxies, not formation of matter that then became those stars and galaxies.
So when you say that there's lots of evidence, and I agree with you about the Big Bang, are you including the cosmic inflation ideas?
Yes. Although the evidence for that is not as strong as the evidence for the overall theory.
Right.
So Rick's referring to a region of time in this tiny little snippet of the universe's evolution when it didn't inflate at a constant rate, but it inflated very quickly, very fast, and then kind of slowed down in its rate, called inflation.
Right. It's like 10 to the minus 36 seconds after that initial state to 10 to the minus 34, where it expanded by a factor of what is it, 10 to the 42, basically went from spherical to being flat. Rapid
The
inflation.
COBE data does give indications of inflation. The fact that you do see temperature variations in the COBE data. I think I have a picture of the COBE data somewhere. No, I don't. I must have taken it out in a later version, earlier version. But the COBE data actually has variations in temperature. There's, pink and blue in the image. And we think that those variations came from this inflation, this really rapid expansion, and that those variations you see are actually quantum variations before the inflation. So they were at the tiny quantum level where there's always variations, but they got stretched so quickly that they then became overall variations in the universe's temperature.
Right, right.
And we're basically seeing a blueprint for the baby universe, a template, if you will, for the seeds of what would be future large-scale structure. During that inflationary period, we have very small fluctuations that form the seeds of future galaxies and galaxy clusters. Am I understanding that correctly?
We think so. That has been the theory, although now the idea that dark matter may have played a role in how the first matter clumped and started
Right.
making these first stars and galaxies, it may be due to dark matter. Unfortunately, we don't know a whole lot about dark matter, and it may be due to dark energy, which caused the dark matter to clump in a certain way or behave in a certain way. So it's just a big unknown, and we're getting there. The James Webb will be part of the answers, but certainly not all of the answers.
Back in the late 1800s, early 1900s, physicists basically thought we had just about figured everything out, right? And of course, Einstein came along and blew all that out, and then quantum mechanics came along, and in the, I don't know, back in the 60s, 70s, we've got all the particles figured out. We've got a pretty good handle on the oh, good grief, Rick, I'm losing my mind. The quantum field theories, all the stuff, all the baryonic matter in the universe. And then to suddenly, after all those years, start to realize that that only amounts to 4.5% of the universe, and it's all this dark matter and dark energy that makes up so much of the rest of it. That, dark matter, I don't think we've got some ideas. They're chasing ideas. They're trying to accumulate enough information to say that it's one way or another, but they truly don't know yet. And dark energy is even further from our understanding than that. And I think that's where some of the drive to get back to some of the fundamentals that we kind of skipped over in quantum mechanics, like the waveform collapse. How does that happen faster than the speed of light, and entanglement altogether? We really don't understand that, and maybe we're gonna have to back up and try to understand those things to really get a handle on dark energy.
It is a tough problem. I see we've got some questions in the chat here. Someone Lee is asking, what observation would most excite you? I think finding life on another planet would be life-changing for all of us on Earth. I don't know if that's going to happen in my lifetime. I really hope so. I think that would be just so exciting. So probably that would be the answer. And then Mylan is asking about hydrogen and helium reionization. It's here on this slide. So what does that mean? It means that the hydrogen gas gets hot enough that it can start doing stuff. It can start forming stars. It can start fusing, and exciting things can happen. It's not just floating around saying, hi, I'm a hydrogen molecule and I'm not doing anything. But when it gets reionized, there's energy involved, and then it means it's getting hotter, and hot hydrogen can lead to star formation.
And photons are released.
Oh, and then Mylan's asking about the reflections off the sun shield. Do they enter The instruments. No. So the sun shield, I mean, that's another hour-long talk and the engineering that went into designing that. But it is designed so carefully that you're not going to have any reflections to worry about. And the fact that that thing was able to unfold all 5 layers successfully is just truly master engineers at work there.
Yeah, you think back to Hubble, and I can remember the summer of 1990. It's hard to believe it's been 32 years now, but it was shortly after Hubble was launched, and then we had the incident with the mirror, and we were all kind of standing around talking about it and wondering if it would ever get fixed and we would ever have a working telescope in space on the scale of what they were talking about. To go from that, and then all the issues, it was basically a 2 or 3 year project to launch a crew up and then have astronauts literally fix the mirror, to this project where the launch pretty much went flawlessly, the deployment of the telescope, and then all of the steps that were involved, basically telescope origami to get the mirror unfolded, and then to get the sun shield, as you were talking about, deployed all 5 layers, and to have it go off without a hitch. And then also the launch itself, correct me if I'm wrong, but the fuel that was conserved in that launch extended the life of James Webb by another 10 or 15 years. I think the initial lifespan was somewhere around 5 years, and now we're up to 20 years potentially. So this what's happened in the last 9 or 10 months from the launch and the deployment of the telescope has been remarkable. I think we're all collectively breathing a sigh of relief, and we can now enjoy the fruits of all of these decades of labor that have gone into it. So to answer the question of what does the $10 billion, what is the payoff of that $10 billion? I would say a flawless mission where we can enjoy potentially 10 or 20 years of new science and in our understanding of the universe.
I know we have a lot of engineers in this group, and I just want to thank you because there's so much engineering that has to go into a project like this. And engineers are good about testing and looking for every failure and testing again. And you look at every scenario that could happen, and it has paid off with this project for sure.
Yeah, and
it's
how can you
gotten
think
some
of everything?
particularly recent experience in that arena, in that she's leading a team of students that are building a satellite that's going to space to do some research into solar cell technology.
Yes, and we've now signed our contract with NASA. So if we don't deliver our satellite, we're in big trouble. We have about a year left, and the engineering challenges are incredible. Even at this small scale, I can't imagine something like the James Webb.
Yeah. I think CubeSats are on board the Artemis 1 mission too, aren't they?
Yes, there are, and I'm sure they're very frustrated that it hasn't launched yet.
Yeah. So that could be interesting too. They'll be deployed near the moon, won't they, when they get into
Yeah,
lunar
these are
orbit?
all lunar-based CubeSat projects, so very exciting, but they're just waiting and waiting for this thing to get off the ground.
Yeah. I think Mylan had another question. It looks like NearCam and MIRI have the same field of view. Is that the case?
I don't have the actual numbers. I kind of knew someone was going to ask that. Thank you, Mylan. But yes, if I look at the sensors and they're about the same locations, yes, they do have about the same field of view. And that's how they're able to combine those images pretty easily. They don't have to do too much cropping. I think MIRI might be a little bit smaller. Its sensor was a little bit smaller than NearCam. So, but still, they're able to get roughly the same amount of sky.
I have lots of questions.
Well, it's good. Now's the time.
So the clumpy, the older galaxies that don't seem to be as beautifully organized, could some of that distortion be due to lensing here and there on its way here, potentially even by dark matter?
Possibly. So these are all Hubble images, and the Hubble is a great telescope, but the resolution, for things this size isn't spectacular. So that's what James Webb's going to find out. They will re-image and look at these young galaxies, the ones that have this great redshift in these images, and they'll check this and they'll see, are they really just the same spirals we see today and we just couldn't tell that before, or are they really different? So hopefully we'll have the answer to that question soon.
And speaking of redshift, on one slide you gave the wavelengths for various absorption, for various elements, but that's before any redshifting. So I had asked the professor from U of M about how narrow these filters are, because if they're looking right at 656 and then that gets redshifted, then you'll miss it, right? So he explained that there are various bandwidth filters.
Right. So
on
I
board.
showed one example and it had a narrow bandwidth, but there's so many filters on there, they can choose the appropriate one to catch the light wherever it might have shifted to.
So my question, kind of following up, is if you can do a continuous spectrum, would they be able to do, instead of a palette, like assigning colors to a palette, or a range of wavelengths, to do a continuous blue shifting so that we would see what these things look like if we were there back then?
I'm not sure I'm understanding. So you want to say take all the blue or all of a certain wavelength range and make a map of like short to long in it within a range?
Yeah, well, I mean, if you have discrete wavelengths, you're going to get one kind of image. But if you have a continuous spectrum of wavelengths and then shifted that according to the distance of the object, that would be possible to see what it would have looked like in visible light if you'd been there back
I
then.
see. It seems
Yeah.
possible, but I don't know that the spectrometer on the telescope would be capable of looking at a large range of wavelengths. It's going to be limited in how much it can take a picture of, right? When the spectrum comes off the grating, it's going to take up space. And so it just depends how much space they had, how much wavelength range they could look at. That's an interesting idea.
Thank you.
Yeah, drawing an analogy to Hubble's tuning fork for the evolution of galaxies, when you look back at some of these that the Hubble Space Telescope captured that are, not as organized, younger, clumpy. I guess what we should not see beautiful spiral structures at a certain point when we look back into the history of the universe. The earliest galaxies, I guess theoretically, should not be beautiful spirals. They should be more irregular in shape. And then later on, closer to our current epoch, we should see more beautiful spirals, more organization, more structure. And then as those galaxies collide, like we see in the antenna, maybe more older and evolved galaxies would be the irregular shape. I know that's an oversimplification, but is that in general what the expectation is when we look back at the history of galaxies?
I think so. I'm not a galaxy expert, but my colleague down the hall is not here on a Friday night because he's got young kids, so I can't ask him. But so Hubble had the idea that galaxies evolved; they changed type as they aged, and then that idea went away when not the Hubble telescope, like Edwin Hubble back in the early part of the 20th century. He thought like spiral galaxies kind of evolved into elliptical galaxies. So spiral galaxies have lots of gas and dust and lots of stars. Ellipticals don't. So he thought there was this natural evolution, kind of like we see in stars. They kind of change and evolve over time. But then as we started looking farther back and seeing younger galaxies, we kept seeing spiral galaxies and elliptical galaxies. So we thought, well, maybe Hubble's wrong. They don't change type over their lifetime. But then we get these clumpy galaxies from the Hubble telescope, and we're like, well, maybe Hubble's right. Maybe they do start differently, and then they evolve into beautifully structured spirals, and then maybe those spirals evolve back into elliptical. So I was saying that the pendulum keeps swinging back and forth on our
Right.
ideas about how galaxies evolve, and that is one of the big questions. And I'm so fortunate. My colleague Dave is a galaxy evolution expert, and he's actually been having students at Rhodes working with James Webb data already. which I wanted to show, but he said no because they're waiting on publication. And I think
Yeah.
a lot of the scientists who have just gotten their James Webb data, it's all going to come out in a big rush. Probably in a couple of months, we'll start seeing the papers, and then some of these big questions are going to be answered pretty quickly.
Right. We're still in the early stages of this. We got to have him back whenever he's available, because this is very interesting. I'm glad you put this slide in here because this really stimulates a lot of thought, because we don't have it down yet as far as, is there a linear progression in the evolution of galaxies, or, is it more, I guess, random or not as organized as we thought. So there's a lot of breakthroughs that could potentially come out from this research.
I think we'll get there. I mean, we didn't understand stars 100 years ago, and now we understand how stars live and die. And now
Right.
the next step is, okay, galaxies.
Speaking of stars, that was kind of my next question. Can we pretty much rule out population 3 stars? The ones that are like, theoretically, we don't know if they exist. They've never been observed to the best of my knowledge, but 100% hydrogen. And then we see, the percentage of hydrogen and helium in POP2 stars, roughly 75-25. Can we pretty much rule out population 3 stars and feel confident that primordial nucleosynthesis is the right picture for, the evidence of the Big Bang? And
Based on what we know today, yes. But what we know 20 years from now, I don't know.
right, that's interesting, isn't it?
So the concentration of hydrogen to helium now, even accounting for stellar evolution over 13.7 billion years, it's 75-25. So that says the Big Bang must have produced roughly that ratio of hydrogen to helium. So a pure hydrogen star could form, but chances are, there's going to be like one helium atom in there or one helium nuclei in there. But hopefully, that's goal number 1 of the James Webb, is to try and find the first stars. And we'll be able to look at their spectroscopic data and we'll be able to tell, are they 25-75 or are they 99% hydrogen?
Yeah, it'd be interesting if one of those was ever observed. That would change a lot of things.
It might change the way those stars evolve. And some of the leading thoughts are that those early stars were really massive, more than 100 solar masses. Today, we never see a star more than 100 solar masses. They just don't form because they're too massive. But maybe in the early universe, conditions were different, and we could have stars forming of 500 solar masses. And the supernova explosion from that kind of star would be very different than anything we've observed so far.
Yeah. It could be, the evolution could be more rapid at that point in time because there's more mass that it's going to burn through. One of the
collapse into black holes.
Right, they could instantly collapse into black holes, right? Yeah, one of the questions I had, how do you find, we're seeing type 1a supernova 9 billion years into the past. And how long does it take for a white dwarf to form? Like our sun, it will take roughly 10 billion
10
years.
billion, yeah.
So how do we find, if the universe is 13.8 billion years old, how do we find type 1a supernova 9 billion years in the past? What process is forming the white dwarf that rapidly?
So maybe those early stars maybe were behaving differently, and you could get a white dwarf, in a second. I don't know.
Right.
Very exciting though to see what we're gonna learn.
I think getting back to Rick's point, really what's come out of the last 25 to 30 years, especially from the Hubble Space Telescope era, is a greater awareness of what we don't know and our ignorance rather than what we do know and think we know. I mean, we go back before that, and there were periods of time, like Rick was alluding to, where we thought we had it all figured out. We had solved everything, and what else is to be discovered? Along comes Hubble, and then they're looking, basically the Hubble Space Telescope. I mean, there was a lot of things it was doing, but its primary mission was to measure the Hubble constant or the Hubble parameter, the expansion rate of the universe. And there were different models. And then in 98, the end result was completely counterintuitive. The universe isn't slowing down in its rate of expansion due to gravity. It's actually speeding up and accelerating. What's causing that acceleration? That's where we get this idea of dark energy, which we think makes up roughly 3/4, 69%, I guess, of the mass energy content of the universe. We have no idea what it is. And of course, we're still looking for dark matter. And now what's come out, correct me if I'm wrong, is there's this crisis in cosmology where two different methods are being used to measure H naught, the Hubble constant. One team is coming up with one result, roughly 73 kilometers per second per megaparsec. The other one is 67, and the error bars don't overlap. And we don't know why. They should agree, or at least there should be some agreement, and there isn't. So we have this crisis in cosmology that hasn't been resolved yet. So as these instruments go out and look at the universe, I don't think it's our knowledge as much as our ignorance that's growing, or at least some of it. So
encourage your children to learn math and study
Yes.
science, because there's a whole lot that still needs to be figured out, please.
Yeah, the Hubble
absolutely.
constant is a big mystery, and the Hubble constant gives us the age of the universe. So it's a pretty important mystery to solve.
Yeah, and then what's affecting it too, the expansion rate today versus what it was in the past. So it's,
And thank you very much. This was incredibly interesting.
yes, it was.
Well, I
Yeah.
hope you learned something new and enjoyed the pretty pictures.
Does anybody have any other questions? We're getting a little past 9 o'clock here.
I think I have a new favorite globular cluster, that one hidden in the tarantula.
It
Yeah.
is something else, isn't it?
I'm curious. I didn't even know there was a cluster there.
I had
Yeah, inside
it
the
is
system.
nice.
That's a beautiful image.
And did you say the Tarantula Nebula is not in our galaxy? Was that something I heard?
It's in the Large Magellanic Cloud,
Oh, okay.
so it's nearby,
Wow.
but technically it's in a different
A
galaxy,
different
but
galaxy. Yeah.
a close by one.
It's only 150,000 light years away, Alan. It's
Yeah.
it's stone's
Yes.
throw away. It's right next door.
Nice. Nice.
Well, all right. If no one else has any other questions, I guess we'll go ahead and wrap up for the evening. And again, excellent talk. I knew it would be good. So
There is one in the chat,
there's one in the chat.
William Peer.
Oh, yes. Hang on.
Oh, can Webb see through the center of the Milky Way? Oh, that's a good question. Except the black hole. So the center of the Milky Way is really dense, and we're kind of stuck in it, right? So there's so much dust and gas. I don't know how much this infrared could penetrate that massive amount of dust and gas, but galaxies give off radio waves, and radio waves are longer wavelengths, so they can penetrate. So we can make a radio map of the Milky Way, and that's been done because hydrogen atoms themselves just give off radio waves. It's pretty amazing. And radio waves are long wavelengths, so they penetrate through the dust and gas. So we do have ways to make a map of the Milky Way, but I don't know that that's on the list of tasks for the James Webb. Good question, though.
That is a good question. We used radio waves to figure out the motions of the stars around what we now know to be the supermassive black hole. I wonder if we could directly image those, some of those with Webb. That is a good question. Okay, with that, yeah, another applause. Thank you very much. A lot of effort went into this presentation. Excellent. I can't wait to
Yes.
watch it again.
Thank you.
Very informative. So with that, we'll go ahead and wrap up. Let me see here. I guess I'll just go ahead and share my screen here for just a second. So again, nothing going on. Oh yeah. Okay. So you talk about government spend. Again, we showed this slide last month to kind of answer the $11 million question. So again, in 2021 alone, the government spent $6.8 trillion. So each one of these little dots here represents $1 billion that was spent. Just take 11 of those and spread those out over 30 years. And that's roughly the budget that went into building this telescope. So almost nothing in comparison. I know it sounds like a lot of money, but compared to what our government, we seem to have an administration that isn't shy about spending money. So yeah, this tool, I think the taxpayers are going to get their money's worth, especially, we'll look back 15, 20 years from now and see what kind of breakthroughs come out of it. But anyway, check out our website if you haven't already. Subscribe to our YouTube channel. Of course, always check out our Facebook group. We've got some good information there. Not much going on this weekend because of the moon and the weather, but Next weekend, we'll send notices out as we get into the month. Again, the 17th, we've got another dark sky observing session coming up if it's clear. September 24, very important date with Village Creek. And then just stay tuned for updates in our email as well as on our website. And with that, I'll just go ahead and release everyone. Once again, say thank you for joining us tonight. Enjoy your weekend, and we'll see you guys at our next event. Have a great night.
Night all.